I'm Dr. Sabna N, Assistant Professor, Department of Electronics and Communication, Rajagiri School of Engineering and Technology, Kagnad, and I'll be discussing a few topics from third module of Antenna and Wave Propagation for S6 EC students. During the class hours, we have discussed the first two modules as well as some of the topics from third module, that is we were discussing linear arrays of n isotropic point sources of equal amplitude and spacing, and we have discussed the two conditions, that is for broadside array as well as end fire array. And now here in this discussion we'll be discussing null directions for arrays of n isotropic sources of equal amplitude and spacing, that is the condition for broadside and end fire, as well as grating lopes and binomial arrays, as well as the design of binomial arrays. So during the class hours we have seen linear arrays of n isotropic point sources of equal amplitude and spacing. So you may please go through those notes, then you can understand the present discussion more. Okay. So the sources are separated by distance d. The figure shows 1, 2, 3, 4, 5 etc. sources. They are separated by distance d, and the angles phi and gamma are measured as shown. So for y-axis, phi equal to 90 degree or gamma equal to 0 degree. Okay. And we have written the expression for electric field E equal to 1 minus e raised to j n psi by 1 minus e raised to j psi, which we have already seen. That is, we have written it as a sum of n terms in geometric progression. Okay. So please go through those notes, try to understand that, and then you will understand this discussion more. So the null directions occur. When will the null directions occur? Null directions occur when electric field E equal to 0. That is, this happens when the denominator is not equal to 0 or the numerator should be equal to 0. That is 1 minus e raised to j n psi equal to 1. What is e raised to j theta? It is cos theta plus j sin theta. Okay. So what when this e raised to j n psi equal to 1 happens? When n into psi is equal to plus or minus 2k pi, multiples of 2 pi, k equal to 1, 2, 3 etc. So from the previous slide we have n into psi is equal to plus or minus 2k pi. Therefore we can write psi as plus or minus 2k pi by n. And we know dr is equal to 2 pi by lambda into d, that is a separation between the sources expressed in radians. So d is the physical separation and dr is the distance between the sources expressed in radians. And we know psi is equal to dr cos phi plus delta, okay, from the previous discussions in the class hours. And here psi is equal to, we are using the notation as phi naught because we are going to find the direction of nulls. Okay, so therefore psi is equal to dr cos phi naught plus delta, which is equal to plus or minus 2k pi by n. And therefore we want the direction of pattern null, so we want phi. Okay, so from expression A we can write phi naught as cos inverse plus or minus 2k pi by n minus delta into 1 by dr. So the expression for direction of pattern null is given by equation B. Now we are considering the separate cases. First we are considering broadside arrays. So from the previous discussions we know for broadside arrays delta equal to 0. So what is delta? Delta is the phase difference of adjacent sources. So for broadside array delta equal to 0. And we can therefore, since delta equal to 0, equation B becomes phi naught is equal to cos inverse plus or minus 2k pi by dr into n, which is equal to cos inverse plus or minus k into lambda by n into d, substituting for dr as 2 pi by lambda into d. Okay, and we are going to replace phi naught by complementary angle gamma 0. This phi is measured from x-axis, gamma is measured from y-axis. So if you are writing in terms of gamma, what happens? This cos inverse, it has to be taken as a complementary. Therefore gamma naught will be sin inverse plus or minus k into lambda by n into d. And for very long arrays, what happens to n into d? N is the number of sources, d is a separation between the sources. So n into d will be much greater when compared to k into lambda. Okay, so what happens to k lambda by n into d? It becomes a very small value. Okay, and for low values of theta, sin theta can be approximated as theta. Therefore gamma naught can be approximately written as plus or minus k into lambda by n into d for very long arrays. Okay, now for first nulls at either side of maximum, occurs for k equal to 1. Okay, so we can we can use the notation gamma not 1, gamma 0 1 for denoting the first nulls. It will be equal to plus or minus lambda by n into d since k equal to 1. And the total beam width of the main lobe between the first nulls for a long broadside array, it is equal to 2 into gamma 0 1. So it is equal to 2 into lambda by n into d. We are considering an example for n equal to 4 number of sources separated by a distance d equal to lambda by 2, and we are considering broadside array, so delta will be equal to 0. And from the previous slide we can write the expression for null direction as phi naught is equal to cos inverse plus or minus k into lambda by n into d. Okay, and we substitute for n equal to 4 and d as lambda by 2, and we'll get it as cos inverse plus or minus k by 2. So if we substitute k equal to 1, what happens to phi naught? We get it as plus or minus 60 degree and plus or minus 120 degree. Okay, and for k equal to 2, what happens? We'll get it as phi naught equal to 0 degree and 180 degree. So we get the 6 nulls for 4 sources separated by a distance d equal to lambda by 2 for broadside array. Okay, so it is plus or minus 60 degree, plus or minus 120 degree and 0 degree as well as 180 degree as shown in the figure. So next we are considering the case of n-fire arrays. For an ordinary n-fire array, delta equal to minus dr. We have already seen that during the class hours. Okay, now equation A for delta equal to minus dr, the equation A becomes dr cos phi naught minus dr is equal to plus or minus 2k pi by n. We are taking out dr outside, so cos phi naught minus 1 is equal to plus or minus 2k pi by n into dr. Okay, and we have the expression 1 minus cos 2 theta by 2 that is equal to sin squared theta. Okay, so we are taking this cos phi naught minus 1, that becomes that becomes sin squared phi naught by 2, which is equal to k into pi by n into dr. The 2 cancels. Okay, and therefore phi naught is equal to 2 into sin inverse root of k into pi by n into dr, and since dr is equal to 2 pi by lambda into d, that is the distance in radians is in terms of actual physical separation d, we get phi naught as 2 into sin inverse root of k into lambda by 2 into n into d. And similar to the previous case, that is for similar to the broadside arrays, for long arrays n into d, that is number of sources into distance between the sources, that is much greater compared to k into lambda. Okay, so therefore k lambda by 2 n d will be a very small value. For small values of theta, very small values of theta, sin theta will be approximately equal to theta. Therefore phi naught can be approximated as plus or minus root of 2 k lambda by n into d. Okay, and for first nulls at either side of maximum occurs for k equal to 1, and therefore phi 0 1 can be equal to plus or minus root of 2 lambda by n into d, and total beam width is twice this phi 0 1. Therefore total beam width between first nulls for a long ordinary n-fire array is 2 into phi 0 1, which is equal to 2 into root of 2 lambda by n into d. We are considering an example of an n-fire array with 4 sources, separation d equal to lambda by 2, and since it's an n-fire array, delta is minus pi. Okay, we are going to find out the null directions using the expression which we have found out previously. Therefore phi naught, which is equal to 2 sin inverse root of k lambda by 2 n d, substituting for n and d, we will get 2 sin inverse plus or minus root of k by 4. Okay, for first nulls, for k equal to 1, so that it will be phi naught will be 2 sin inverse plus or minus 1 root of 1 by 4. So it is 2 into sin inverse 1 by 2. So sin inverse 1 by 2 is 30 degree. Therefore 2 into 30 degree, which will be equal to 60 degrees. So similarly we can find out for k equal to 1, k equal to 2, k equal to 3, etc. So we get the nulls. Okay, so plus or minus 60 degree, plus or minus 90 degree, and plus or minus 120 degree. Okay, so as seen from the figure, we have 6 nulls. Okay, that is for an n-fire array. Next we are summarizing the results, that is null directions and beam widths between first nulls for linear array of n isotropic point sources of equal amplitude and spacing. So we have considered the general case, phi naught will be cos inverse 2k pi by n minus delta into 1 by dr. That is a null direction phi naught. Okay, and then we found out for broadside array gamma naught will be equal to sine inverse k into lambda by n into d, and first null gamma naught 1, it is lambda by n into d, and beam width is twice the null direction 2 into gamma naught 1. So it is 2 lambda by n into d, and for ordinary end fire we have found out phi naught, that is 2 sine inverse root of k lambda by 2 nd, and the first null phi naught 1, it is root of 2 lambda by n into d, and beam width is twice the phi naught 1, this 2 into root of 2 lambda by n into d. Okay, and we have seen that this phi is measured from x-axis and gamma from y-axis. Okay, so for and broadside array, the beam width will be 2 into gamma naught 1, and for an end fire array it is 2 into phi naught 1. Okay, next about grating lopes. It's a term used for secondary main lobes in the antenna diagram. Okay, they are very strong side lobes, or you can say grating lobes are unintended beams of radiation. Okay, and they have approximately the size of main lobes, and grating lobes are as a consequence of too large distance between the individual radiator elements relative to the wavelength. Okay, and grating lobes are typical for arrays with inter-element spacing of lambda or more, and we can define a grating lobe as it's a lobe other than the main lobe produced by an array antenna when the inter-element spacing is sufficiently large to permit in-phase addition of radiated fields in more than one direction. Okay, and by a good design of an array, grating lobes will vanish. Okay, for broadside array, to avoid a grating lobe, the largest spacing between elements should be less than one wavelength, that is Tmax less than lambda. And for an ordinary end fire array, to avoid grating lobe, the maximum spacing between the elements should be less than lambda by 2. So till now we have been considering arrays with uniform amplitude distribution. That means all the sources are fed with same amplitude current. Now we are going to deal with arrays with non-uniform amplitude distribution. Okay, that is uniform spacing but non-uniform amplitude distribution. So we were previously considering uniform distribution. Now we are going to see more about other distributions, that is binomial and Chebyshev. And of the three distributions, that is uniform, binomial and Chebyshev, a uniform distribution yields the smallest half power beam width, or you can say that they gives the maximum directivity, and it is followed in order by Dolf-Chebyshev and then binomial arrays. And in contrast, binomial arrays possess the smallest side lobes, followed by Dolf-Chebyshev and uniform arrays. Or you can say that binomial arrays with inter-element spacing equal or less than lambda by 2 have no side lobes at all. So we can conclude that the designer must compromise between side lobe and beam width. And for a given side lobe level, Dolf-Chebyshev array produces smallest beam width between the first nulls. Conversely, for a given beam width between the first nulls, Dolf-Chebyshev design leads to the smallest possible side lobe level. Okay, and you can learn more about Dolf-Chebyshev arrays and their design, etc. in the class given by Rinjumis. So linear arrays of equal amplitude isotropic sources were discussed previously. Here we discuss the more general case of non-uniform distributions. Okay, a uniform distribution yields the maximum directivity or gain, but the side lobes are large. So to reduce the side lobe level of linear in-phase broadside arrays, John Stone proposed that the sources have amplitudes proportional to the coefficients of a binomial series of the form shown, where n is the number of sources. Or you can say that for binomial arrays, the relative amplitudes are as given by the Pascal's triangle. Any inside number is equal to the sum of the adjacent numbers in the row above. Okay, so for 3-element array, the amplitudes or the relative amplitudes are 1, 2, 1. For 4-element array, it will be 1, 3, 3, 1. For 5-element array, it is 1, 4, 6, 4, 1, etc. So we are considering normalized field patterns of broadside arrays of 5 isotropic point sources spaced lambda by 2 apart. Okay, and all sources are in same phase but have different relative amplitude distribution. Okay, so we compare the performances of uniform array with binomial distribution and Dolch-Chebyshev. Okay, so uniform distribution for 5 elements, the relative amplitude distribution is 1 1 1 1 1, and the beam width is approximately 23 degree. For binomial distribution, it is 14641. We see that the beam width is 31 degree, but there are no side lobes. And for Dolch-Chebyshev, it is around 27 degree with smaller side lobes. Okay, so we see that for binomial distribution, the pattern has no minor lobes at all, but this has been achieved at the expense of an increased beam width, that is 31 degree compared to the other distributions. Okay, and for spacing of lambda by 2 or less between the elements, the minor lobes are eliminated by the Stone's binomial distribution. However, increased beam width and larger ratio of current amplitudes required in large arrays are disadvantages. Next, about the design procedure of binomial arrays. Binomial arrays do not exhibit any minor lobes provided that the spacing between the elements is equal to or less than lambda by 2. And expressions for half power beam width and maximum directivity for d equal to lambda by 2 have been derived and it is available in textbooks, and it is as given. Half power beam width is approximately equal to 1.06 by root of n minus 1, or it is 0.75 by root of L by lambda, where n is the number of sources, L is the length of the array, and lambda is the wavelength of operation. And maximum directivity, it is approximately equal to 1.77 into root n, or it is 1.77 into root of 1 plus 2 L by lambda. And these expressions can be used to design binomial arrays with the desired half power beam width or directivity. Moving on to the steps of designing. Now the first step, finding out the amplitude excitation coefficients either using binomial series or Pascal's triangle. So we have seen the Pascal's triangle earlier. So for 4 element sources, the relative amplitude distribution is 1 3 3 1. For 5 elements, it is 1 4 6 4 1. We have already seen. And then find out the directivity and similarly half power beam width from the using the equations which we have seen in the previous slides. Okay, and finally side lobe level, that is for binomial arrays, if the inter-element spacing is less than or equal to lambda by 2, there will be no side lobes at all. Now we shall see a small problem. For a 10 element binomial array with a spacing of lambda by 2 between the elements, determine the half power beam width in degrees and maximum directivity in decibel. So for 10 element array from the Pascal's triangle, we see that the relative amplitude distribution should be as shown, that is 1 9 36 84 126 126 84 36 9 1. Half power beam width using the expression which we have seen previously, that is 1.06 by root of n minus 1, it is approximately 20.23 degrees, and maximum directivity, it is 1.77 into root n, it is approximately 7.48 decibel. Now these are the references. Okay, so we have seen almost 3 modules during the direct class hours, and then the remaining modules I have shared with you the PPT with audio as well as other notes. Okay, and I have also shared previous university question papers and the answer keys also, some of them. So please go through those and make maximum use of those. Okay, and make sure that you learn, you cover all the topics which were asked in the previous question papers. Okay, and cover important problems also, and all the best for your exams. Thank you for your patient listening.